Welcome everybody, I am Lars and I will talk about structural parameterizations of Clique coloring. This is a joint work together with Paloma Lima and Gevarghese Philip. So first, what is a Clique coloring of a graph? Well, we all know that a proper coloring of a graph is an assignment of colors to its vertices, such that whenever two vertices are adjacent, then they receive different colors. In a clique coloring, what we care about are the maximal cliques of the graph, and we require that no maximal clique is monochromatic. This means that in any maximal clique, we have at least two colors. So if we look at this one in the example, then we see that both color blue and color yellow appear on its vertices. So this one is fine. And similarly, on the other one, we both have a blue vertex and a yellow vertex. So this coloring is indeed a clique coloring. Now, clique colorings behave quite differently from proper colorings. For example, we can destroy a clique coloring when we take subgraphs. So if we remove this edge, for example, then this coloring is not a clique coloring anymore, because here we have two monochromatic maximal cliques. And even when we take induced subgraphs, this might happen. So now we remove the vertex in the top left, and we also have a monochromatic maximal clique in the graph. Okay, so again, a vertex coloring of a graph is a clique coloring if there is no monochromatic maximal clique, and the clique chromatic number of a graph is the minimum number of colors in any of its clique colorings. So also observe that taking induced subgraphs can even increase the clique chromatic number of a graph and not just destroy clique colorings. So whenever we have a universal vertex in a graph, then we only need two colors. So we can assign one color to the universal vertex and the other color to the remaining guys. And since the universal vertex is contained in every maximal clique, this will always be a clique coloring. On the other hand, if we remove this vertex, then in this example, we end up with a C5, and a C5 always needs three colors. Okay, now some complexity results about the problem of finding clique colorings. Well, it has been shown to be co-NP hard to verify if a given two coloring of a graph is a clique coloring. And this is very much in contrast to proper colorings, where we can famously compute in polynomial time if a graph is two colorable or not. And then later on, it was even shown that for any fixed number of colors, the clique coloring problem is sigma 2 complete. On the positive side, it has been shown to be solvable in roughly 2 to the n time on n vertex graphs. And there are several polynomial time cases on restricted graph classes, such as planar graphs, circular arc graphs, and graphs that have few P4s, such as co-graphs, P4 sparse graphs, and some other cases. Now, in all of these cases, it is actually shown that you can always color the members of the graph class with at most 3 colors. And one very central conjecture in the field of clique colorings was that all perfect graphs can be clique colored with at most 3 colors. For the longest time, this was believed to be true, also because for many subclasses of perfect graphs, this conjecture has been confirmed. But finally, in 2016, it was refuted by Shabi and others who showed that perfect graphs may actually need an unbounded number of colors in a clique coloring. Okay, in this work, we consider the clique coloring problem parameterized by structural measures of the input graph, and the first one is the tree width. So specifically, we consider the Q clique coloring problem parameterized by tree width, where we are given a graph together with one of its tree decompositions, the parameter is the width of that tree decomposition, and the question is, does G have a Clique coloring with Q colors? Now, we know that there is always a Clique coloring with tree with +1 many colors, which is why we consider the problem for a bounded number of colors, because in this case, it's in Clique coloring, this is the more interesting case. So what we show is that for any fixed Q, at least 2, Q Clique coloring parameterized by tree width can be solved in roughly Q to the tree width time. But this is also tied under the strong exponential time hypothesis. So for the upper bound in this theorem, we give a standard dynamic programming algorithm where at some point we have to use fast subset convolution. And for the lower bound, we give 2 reductions, one for the case where the number of colors is at least 3, in which case we can use hardness results for proper coloring parameterized by tree width, and we give a separate reduction for the case of 2 colors. So after that, we also consider the Clique coloring problem parameterized by the Clique width of the input graph. And in this parameterization, we give an algorithm that runs in time k to the 2 to the 2 to the Clique width, where k is the number of colors that is being asked for, and n is the number of vertices in the input graph, and CW the Clique width. Now for unbounded number of colors, this is an XP runtime. So that means the runtime is roughly n to the 2 to the 2 to the Clique width. And for a bounded number of colors, this is FPT. But Clique coloring is also expressible in MS01. So the FPT result already follows from the meta theorem of Korsell, Markowski, and Ortiz. All right, so I will explain a bit how the tree width results come about. And to do that, I will first show you in a nutshell what is the tree width of a graph. So suppose we have this graph, which looks intentionally a bit like a bicycle. Then a tree decomposition of this graph is obtained by putting the vertices of the graph, subsets of the vertices of the graph into bags. And then we arrange these bags in a tree-like structure. And this tree decomposition has to satisfy 3 properties. First of all, every vertex has to be contained in at least 1 bag, which is the case here. Second of all, each edge of the graph, for each edge of the graph, there is a bag containing both of its endpoints. Also, this is satisfied here. And finally, if we look at every vertex of the graph and the bags that contain that vertex, then these bags induce a connected subtree of the tree in the tree decomposition. So here, if we look at this vertex, it appears precisely in those 3 bags, and they are connected. Now, the width of a tree decomposition is the maximum bag size minus 1. In this case, it's 5. And the tree width of a graph is the minimum width of any of its tree decompositions. Okay, so in our algorithm, we do a bottom-up dynamic programming, and we assume that the tree decomposition is rooted in some arbitrary bag. And so for each bag, we will store some information that mostly concerns 2 things. First of all, what happens in the top bag, and second of all, how does this interact with the rest of the graph that is induced by the vertices that appear in bags below. So here in the top bag, we have these yellow vertices, and some of them may appear in some of the children, and then there are some bags that do not contain any bags from the top bag, any vertices from the top bag anymore. So we will depict this like this. This will be the top bag, and this triangular stuff, the rest. Okay. So what do we store? So our first attempt would be, we just look at any coloring of the vertex in the top bag and we ask, can we extend this coloring to a Clique coloring of the graph below? So this means that whenever we have a monochromatic clique in this coloring, it cannot be a monochromatic maximal clique, right? Okay, but this is not really sufficient because there are still some vertices that appear later up in the tree decomposition, and they might influence the coloring of the vertices in the top bag. So for example, if we have a monochromatic maximal clique like this in the top bag, then maybe there is still some vertex later on in the tree decomposition that is adjacent to all of them. And then we may decide to give this one another color, and we don't have a monochromatic maximal clique anymore. So in this case, we cannot disregard this coloring. So on the other hand, if we have a monochromatic maximal clique that uses vertices from the graph that is strictly below, so vertices that are not contained in the top bag, then we know that these vertices do not have any neighbors in the rest of the graph. This follows from basic properties of tree decompositions. And so in this case, we know that this clique will never become, so this clique is already a maximal clique, and we cannot allow this situation in any coloring that we consider. So we can tolerate monochromatic maximal cliques, but only if they're fully contained in the top bag. And then what we store is that for any coloring of the top bag, we ask, is there an extension of the coloring to the vertices below, such that all monochromatic maximal cliques are fully contained in the top bag? Okay, so at each node, this means that we have to consider at most q to the tree width plus 1 colorings. And then we need to be able to check efficiently if some subset of the vertices in the top bag contains a maximal clique in the subgraph below. And this is where we have to use fast subset convolution, because otherwise we would blow up the runtime of the algorithm prohibitively. But okay, then if we have an efficient implementation of this, then we also have a q to the tree width total runtime. And we have this upper bound part of the tree width theorem. All right, for the lower bound, let's consider the case when we have at least 3 colors. So first we can observe that in any triangle-free graph, the proper colorings and the clique colorings coincide. And this is simply because if we don't have triangles in a graph, then the maximal cliques are precisely the edges, which means that we forbid monochromatic edges, which is what happens in the notion of a proper coloring. Now, by a theorem of Log-Stanov and others, we know that Q list coloring parameterized by tree width cannot be solved in time Q minus epsilon to the tree width unless strong ETH is false. And actually, if you look at their reduction more closely, this also holds for triangle-free graphs. So basically all we have to do is we have to get rid of the lists while keeping the resulting graph triangle-free. Okay, and I will explain how we achieve that. Okay, suppose we have this graph here. It's just 2 vertices that are connected by an edge, and each of these vertices has a list. And we are looking at the case when we have 3 colors. Now, if we can have triangles, then there's a very simple trick of how to get rid of the lists, which goes as follows. So we add a clique to the graph where each vertex of the clique corresponds to 1 color in the Q coloring instance. So in this case, we add a clique on 3 vertices. And then whenever a color does not appear on the list of a vertex, we make it adjacent to a vertex of the clique that represents this color. So for instance, here we don't have color red on the list, so we make this vertex adjacent to the vertex in the clique that represents color red. Okay, so now basically we have to achieve the same thing but without introducing triangles. And for this we use Misielski graphs. So these are a family of graphs that contain for every integer k a uniquely k-colorable graph that is also edge critical. So here we look at M4, which is a uniquely 4-colorable graph, and edge critical, meaning that whenever we remove an edge, we obtain a 3-colorable graph. So now we know that in any proper coloring, in any proper 3-coloring of this graph, these two vertices need to receive the same color, right? Because otherwise we would have a 3-coloring of M4, which does not exist. So now the idea is that we get 3 copies of this guy such that each of these copies is responsible for blocking 1 color from the list of a vertex. All right, and this is obtained as follows. So first we have to make sure that each of them is responsible for a different color, right? So we have to connect these copies somehow, but again, we have to make sure that we don't introduce any triangles. So to that end, we introduce some true twins of these special vertices. And we also know that each of these, false twins, they cannot be adjacent. And we also know that each of these false twins will have to receive the same color as these 2 special vertices for the same reason as above. Okay, and now we use these newly introduced vertices to connect these copies. Now, here we have this blue vertex, which is adjacent to a yellow vertex, meaning this guy cannot have color yellow. But since all of these 3 guys receive the same color, we know that none of these guys can receive color yellow, right? And here we have a vertex, a blue vertex that is connected to red. So we also know that none of these can receive color red. So this means that we finally obtained what we're looking for. We can use this vertex to block color blue, this vertex to block color yellow, and this vertex to block color red. Okay, so now how to use this gadget? Well, suppose we have a vertex whose list consists only of color blue. Again, we cannot connect this vertex directly to the gadget because we would be risking some triangles. So instead, we introduce 1 new vertex for each color that we want to forbid. And we connect them to this gadget in the good way. So for example, this vertex is responsible for blocking color yellow. So we make it adjacent to the vertex blocking color blue and the vertex blocking color red. And then we know that this guy must receive color yellow in any proper coloring, meaning that this guy cannot receive color yellow. Same for the red guy. And now the tree width increases by at most 3 times the number of vertices of M4, which is a constant because M4 is a fixed graph. All right. This finishes the reduction for at least 3 colors. And for 2 colors, well, we know that 2 coloring is easy, so we cannot really use the same strategy. Instead, we give a reduction from the not all equal set problem. And this problem has a strong ETH-based lower bound, which was shown by Sigan and others a few years back. Okay, and this finishes the lower bound part of the tree width result. Okay, so now I will briefly talk about the clique width algorithm. And so first of all, what is clique width? Clique width, so tree width is unbounded already on very simply structured dense graphs, such as complete graphs. And clique width generalizes tree width, and it remains unbound. It remains bounded. Sorry, here it says unbounded, and it is bounded on simply structured dense graphs. Now, in our algorithm, we work with the equivalent measure module width, and so this is linearly related with clique width, meaning that obtaining results for module width are, pretty much the same as obtaining results for clique width. This measure is defined as follows. So we have, let's look at this graph G. Then we look at the rooted branch decomposition of G, which is basically a binary tree such that the vertices of G are mapped to the leaves of that tree. Okay. Now each edge of this tree induces a cut of a graph where we can look at the vertices that appear in the subtree hanging below and the rest of the graph. So this cut, in this cut, we have the vertices A and B below and CDE on the other side. And now we measure the complexity of the cut in the following way. So we say that two vertices in the graph below are equivalent if they have the same neighbors on the outside. And then the complexity of the cut is just a number of equivalence classes we have in this equivalence relation. So here, this complexity is 1 because the vertices A and B are equivalent, right? They have the same neighbors. On the other hand, if we look at this cut, then we have the vertices D and E below, and these two vertices are not equivalent because D is adjacent to C, but E is not. Okay, the module width of a rooted branch decomposition is the maximum number of equivalence classes in any cut, and the module width of a graph is the minimum module width over all its rooted branch decompositions. So how does our algorithm work? Well, we do dynamic programming along the rooted branch decomposition, and partial solutions at a node are colorings of the vertices below. And what we will do is that we group color classes into types, and then instead of remembering the whole coloring, we show that it's enough to remember for each type how many color classes of the type there are. So this is what we call the signature of a coloring, and if two colorings have the same signature, then they are interchangeable for the sake of the algorithm. And to see where the runtime bound comes from, we will see that there are 2 to the 2 to the W many types, where W is the clique width. And then this immediately translates to an upper bound of K to the 2 to the 2 to the W for the number of table entries. Okay, so what is a type? So we will be considered with the following situation. So we have some cut and some vertices that are below. And these vertices are grouped into equivalence classes according to their neighborhood on the outside. Now, suppose we have some subset of these vertices that will be a color class in a coloring. Then what we keep track of is monochromatic cliques in this color class that may become maximal at some point, or maybe they are already maximal. And we describe these cliques in terms of their profiles, where a profile records for each equivalence class a constant amount of information. For example, we may record that, okay, in this clique, we have some vertices inside the intersection of the equivalence class with the color class. And then there will be some other stuff, but in the end, it's a constant amount for each equivalence class. So there are 2 to the W many profiles in the worst case. And then a type of a color class is simply the subset of profiles such that there is a clique with that profile. And this is why we have this double exponential dependence on the number of equivalence classes. Okay, so to conclude, we considered clique coloring parameterized by tree width and by clique width. And let me finish with some open problems. So the most pressing one is probably the question whether clique coloring parameterized by clique width is W1 hard or not. And so we believe the most feasible route towards an FPT algorithm would be to show that there is a function G such that all graphs of clique width W are clique colorable with at most G of W many colors. Okay, but even if it turns out to be FPT, it might be that this triple exponential dependence on the clique width is optimal. So to see if this is really the case, we could, for example, try to give an algorithm that solves two clique coloring parameterized by clique width in something that is less than triple exponential. So therefore, we also pose this as an open problem. Okay, so thank you very much. That was it.